Hello, my name is Louis Pritchett, and the presentation you're about to see is on the construction and operation of a decade or modulus 10 counter. This particular circuit will be able to count from 0 to 99. This is the 7493 counter chip and its pin diagram. The pin assignments are as follows. Pin 1 is clock B. Pin 2 is reset 1. Pin 3 is reset 2. Pin 4 is normally closed and will not be used. Pin 5 is the 5-volt input. Pin 6 is normally closed and will not be used. Pin 7 is normally closed and will not be used. Pin 8 is the Q2 output. Pin 9 is the Q1 output. Pin 10 is ground. Pin 11 is the Q3 output, which is the most significant bit. And pin 12 is the Q0 output, which is the least significant bit. Pin 13 is normally closed and will not be used. And pin 14 is clock A. This is the logic diagram of a mod 10 counter circuit, where Q3 is the most significant bit and Q0 is the least significant bit. Since all 4 bits will be used on both chips, clock B has to be wired to Q0. Because this is a mod 10 counter on both chips, Q3 and Q1 will need to be high in order for the counters to reset. And this is accomplished by wiring Q1 to reset 1 and Q3 to reset 2. To begin wiring this circuit, I first connected the ground pin to ground. That was pin number 10 to ground. And then I connected pin number 5 to a 5-volt source. Next, I wired the Q0 output, pin 12, to clock B, pin 1, on both chips. And again, the reason for doing this is because we're using all 4 bits on each chip. Then I wired the most significant bit on pin 11 to the reset number 2 on pin 3. Again, I did it on both chips. Next, I wired pin 9, which is the output Q1, to pin 2, which is the reset number 1. I did this on both chips. And again, the reason why I wired Q3 and Q1 to outputs R2 and R1 respectively on both chips is because these pins have got to see a high signal in order for the counter to reset at 9, which would make it a modulus 10 counter. Next, I wired pin 14 on the chip on the left to the defound switch. This is the input to the circuit. Then I wired its output, pin 11, to the input of the chip on the right, which is pin 14. Then I connected the Q outputs of the chip on the left to hex display 1, connecting Q3 through Q0 to H0 through H3 respectively. Then I connected the Q outputs of the chip on the right to hex display number 2, connecting outputs Q3 to Q0 to hex display H4 through H7 respectively. The yellow wire is a connection between the D-bounce switch, which is normally open, to the clock A input of the first counter chip, which is on the left. For each press of the D-bounce switch, the counter advances 1 digit. In the lower right, you can see how the chips were wired to the hex displays. The upper wires, which are blue, represent the chip that was on the right. And the lower wires, which are white, represent the connections for the chip that was on the right. This is how the overall circuit looks after it has been constructed. In order to test this circuit to make sure it is working correctly, you would have to press the D-bounce switch, which is normally open, and advance the counter. If you press the switch one time, the hex display on the lower left should indicate that 1 count was received by the circuit. In this case, the counter, or the D-bounce switch was pressed 19 times and displayed in the hex display on the lower right. In order for this counter to work properly, for each press of the D-bounce button up until 99, every digit should be represented. If any digit is skipped, the circuit is not wired properly. And after it reaches 99, it should reset to 0. Thank you. What I've just presented to you is the construction and operation of a Mod 10 counter.